The growing field of silicon photonics aims to integrate optical and electrical functionality onto a single silicon chip in order to overcome some of the limitations of the traditional, purely electrical solutions in communications and computing. Further, silicon photonics offers novel solutions to other problems. For example, it gives the possibility of developing simple and low-cost sensors for use in the industrial or biomedical fields. The optical devices made on silicon chips are often very small in size, and this is one of the reasons why photonics is so appealing. That is, many devices can be made to occupy a very small amount of space. However, the small device size comes with the same problem that we see in ever-shrinking electrical components. That is, their performance then depends strongly on even tiny variations in device dimensions. As such, in order to make devices with very predictable performance and the smallest variation from device to device, expensive fabrication techniques and processes that give fine control over component dimension are often used. My project focuses on one approach to allow the fabrication of devices using cheaper techniques that give less control over device dimension, and as such, more variability in device output. However, if we can make devices sufficiently reliable with these cheaper fabrication techniques, then the number of applications for silicon photonic solutions may increase dramatically. How this approach works is, in addition to being highly sensitive to device dimensions, the behavior of photonic devices depends strongly on the temperature of the device itself. It has been proposed that by locally heating each device on the silicon chip, we may individually tune the performance of each device to compensate for any variation from fabrication. My project involved the design of devices that have a strong, measurable response to temperature changes, and the design of a variety of local heating elements. If this approach to making devices to be practical, the heaters must be efficient. By this I mean that the heater should require as little power as possible to adjust the performance of the devices to within specification. I intend to determine what heater designs give the greatest control over not just the amount of heat produced for a given power, but also the greatest control over the distribution of heat, by making sure that there is enough heat, and also that the heat is going to where it will have the greatest impact. The strongest device response can be achieved for the minimum input power requirement. Ultimately, the design of efficient local heaters can make thermal tuning a promising solution for low-cost yet reliable devices. Thank you.